All right. Well, good morning, everybody, and welcome back to school. It's been quite a year. I feel it's just been like, I don't know. So anyway, this is going to be. Oh, I got the wrong letter here. It's 102C. 102C it should say that. Okay. 102C. Okay. So I guess we'll. I think you guys all know how to use Zoom, but just in case, I do make use of a couple features here. So I think everybody here is muted, which is great. And a lot of you have your cameras on, which is also great. Some of you don't have your cameras on, and that's okay. But you know, my preference is to see your faces. It's always much better that way. And I think you guys can see each other's faces too, right? Like you can do the split screen business where like part of it is my slide and then the other part is like your classmates. And I think it's always nice to see your classmates, right? So so anyway, I encourage you guys to turn your cameras on, and we'll do that. There's a participants thing. Okay, so I think across either the top or the bottom of your screen, there'll be a participants button, and you can click that, and that'll pull up a panel of everybody who's in the room. And then at the bottom of that panel, I think there is a button to raise your hand. And then there's also some feedback buttons where you can say things like yes, no, go faster, go slower, and things like that. So why don't you guys go ahead and just click some random feedback buttons. It doesn't matter. Give me some thumbs up or whatever. People are saying go faster. All right, that's fine. Okay. Oh, and you guys have also discovered the reactions buttons, some of you, and with the new version of Zoom, you now can like do like party emojis and stuff like that. Okay. And then there's the chat, which you guys can throw questions into the chat, and I try to pay attention to that. So you know, whatever you want, do that. Okay. And then during office hours, if you need to have a private discussion, I can put everybody into the waiting room, and we can have, or everyone else in the waiting room, I suppose, and then you can still have a private meeting if necessary. Okay, and then I think you guys are allowed to schedule your own meetings at UCLA. Oh, you know what? Oh wait, no, I am recording. I am. Oh, hang on. Is my audio on? Somebody unmute themselves and say hello, because I'm not sure if something.
Hello.
Oh, okay, okay. All right, I can hear you. Great. All right, and you know, I think if you want to ask a question audibly, I think it could work. You can throw it in chat, or you can also just unmute yourself and ask a question. I think that could work as well. All right. This is I think this is what I've put in the syllabus. So the plan for office hours is I'm going to have them Thursdays and Fridays. Thursdays from 3 to 4, Fridays from 1 to 2. And we'll just use the same Zoom link that you're using now. So whatever you clicked to come in here, use that for office hours. And you can call me. Oh, I'm sorry, I didn't introduce myself. I'm Miles Chen. I think many of you have had me as a teacher before, but maybe some of you have not. And you can call me Miles or Professor Chen or Dr. Chen or whatever you want. Okay, so whatever you're comfortable with, that's fine. All right, we have a couple textbooks that I will be using, and both of them doing Bayesian data analysis. Let's see, will this work if I click? Okay, right now I'm not connected to the VPN, but if you're connected to the VPN, this textbook and the next textbook, both of them, as long as you're connected to the UCLA VPN, you can download the PDFs for free. Okay. If you're not connected to the VPN, you're going to get this link that says buy the textbook for $60 or something like that. But part of your tuition that you're paying goes to the UCLA library, and then the library subscribes to these different services, and one of those services gives you textbook access. So you should be able to download these PDFs as long as you have to be connected to the VPN. So make sure you have that set up. And if you want your physical book, you can purchase a physical book, but that's not necessary, right? All right, so this is the plan for grading. Okay, I'm going to have lecture viewing quizzes, and I'll explain how that works. Homework assignments, and then I'm planning, the current plan is to have 3 exams, okay? Exam 1, 2, and the final. And then campus wire participation, and that should add up, I think that adds up to 100% there. Okay, so and grading scale is a straight scale. I don't curve. That's kind of how it goes. Okay, so the whole idea with lecture viewing quizzes, and I have to set up today's lecture viewing quiz, but basically it's during the lecture, I'm going to kind of drop a couple multiple choice answers, and it's just intended that as long as you kind of watch the lecture and follow along, you should get pretty much 100% on the lecture viewing quiz. It should be easy. The viewing quizzes are open only for kind of a short period of time, and this is to kind of make sure that you at least watch the lecture, even if you're not able to attend live, just to make sure that you do watch the lecture and not fall behind, because you know, when you take an online course, it's tempting to skip a class and then fall multiple lectures behind, and it's misery trying to binge watch lectures. You know, it's fun to binge watch TV, but lectures, it's quite terrible. Okay. As far as homework goes, I kind of have this weird late policy for homework. Basically, you turn it in on time, you get no deductions, and then if you're more than 10 minutes late, you get 5 points off, and basically every hour after that is another 5 points off. But deductions stop at midnight, and then they resume the following day. So, and then if you need an extension, if you submit documentation with your homework assignment, you'll get a 72-hour extension. Okay, you don't have to email me directly if you've got some documentation to go along with it. And then as far as office hours go, I love when students come to office hours. The one thing that I'm not too enthused about is when, getting in arguments over how many points a mistake is worth. But if you feel like it's a necessary discussion, we can do that. And of course, if we made a mistake in grading, like the TA, the grader, or myself, marked something wrong that was right, of course you can come to office hours to get those points back. That's not a problem. It's just every now and then I get a student will say, you took off 10 points for this mistake, and I think the mistake should only be worth like 6 points or something. And it's kind of an impossible argument to have in terms of what goes on. As far as homework goes, there's going to be a lot of coding. Okay, there's going to be a lot of coding. Just expect that. If you've taken a class with me before, I think you can, and you have a sense of what my homework assignments are like, and they're fairly long. They're kind of I don't know. I think you have to write quite a bit, and I like to think of this. In order to graduate UCLA, you have to fulfill a writing 2 requirement, which is basically some class, any class. It's not necessarily a writing class, but it's a class where a lot of the assignments are writing related. And similarly, this is not a requirement to graduate UCLA, but I do think it's kind of it should be a requirement for anybody who plans on going into data, is to you have to become proficient in writing code. And the only way you really become proficient in writing code is to actually write code. So there's lots of code writing that I do assign in the homework, and that's just that's by design. Okay, so I do want to just take a moment to talk about academic integrity and plagiarism. And so, all of the assignments that I give, some of the tasks and things have already been solved. Okay, I'll ask you to write some code to perform some kind of algorithm. Okay, so at some point we'll learn about like the Metropolis algorithm or the Gibbs sampler, and these are known algorithms and known kind of systems that have been around for a while, and you'll find code out there that does exactly what I'm asking you to do. Or there's already packages and things like that. Okay. And if you're working and the important mission is to accomplish a task, then of course you should use the readily available packages or code solutions, these things that already exist. Okay, there's no need to reinvent the wheel when you're working on a job. Okay, but the difference is this class, the goal is not for you to accomplish whatever task I set out in the homework, but the goal is for you to kind of learn that. To learn the process or to learn the algorithm, whatever it is that we're teaching. Okay, and so for that reason, I think it's important that you work through the homework itself. Okay, and my apologies to every student who's taken a class from me before and have already heard this spiel, but it's important to me, and I like to kind of go over it each time. So if you think about going to the gym to work out, there's a kind of a common saying that goes around, and it's this idea of no pain, no gain. And the reason why people go to the gym is not so that weights in the gym get lifted. Like if somebody lifts weights in the gym, it's the purpose of doing that is not so that the weights get lifted. The goal of lifting the weights is the actual process of lifting the weights, which tires out someone's muscles so that later on their muscles come back stronger and the person gains strength. Okay, and basically, if the workout was not intense enough, that it was super easy for the person to go through the workout, then that person can't expect to make progress or see gains in the gym. Okay, and similarly, when you write code, if all of your code writing is so simple that your brain is not challenged, your brain is not going to see the need to try to get better or make new connections. And so if you do during the homework assignment, you do see it as, if it is a challenge to you, that's a good sign, because that means your brain is struggling, and then that you'll have to create some new connections between the neurons, especially when you sleep. So sleep is important. And then and your brain will get better and you will become a better coder. And that's kind of the process. And so, if it comes to plagiarizing, so, let's say you get a homework assignment and it's tough for you, my encouragement is for you to kind of stay with it and try to work through it. And not to kind of take a shortcut, not to peek at somebody else's solutions or something like that, because you know, if you do that, you're effectively asking someone else at the gym to lift the weights for you. Okay. And of course, if somebody else lifts the weights at the gym for you, you cannot expect to get better yourself or stronger yourself. And that's kind of what's going to happen if you look at someone else's code or plagiarize or look up solutions. Okay. And so, you know, I'm not here to try to like shame anybody and say that, you know, students who copy code and cheat or something are like these evil people. Okay. I don't think that's the case. I think what happens in these cases is that students kind of mix up the priority of, you know, this task needs to be accomplished versus I need to struggle through this to learn it. Okay. And so, you know, getting kind of completing the homework assignment to get, you know, some desired grade, if that becomes the priority over the learning, you know, that's going to kind of, you know, then plagiarizing becomes, you know, more of a desirable option. Okay. And I have to admit that a, you know, major conflicting issue is that I can't create some kind of individualized grade schema for each individual student to kind of see and measure how much each individual student has learned over the time of the course. And everybody's kind of graded on the same criteria and, you know, what it is that you've turned in. But, you know, my hope is that you yourself can kind of judge your own performance based on what you've learned and not necessarily what letter grade you end up with. So that's what I'm hoping for you guys. Okay. And so, you know, as far as the homework assignments go, you know, my expectation is that you're going to work hard and not try to seek out solutions online or not, you know, look up someone else's code or something like that. Okay. And I want you guys also to be okay with the idea of, you know, if the homework assignment is not 100% complete, you know, turn in what you have, you know, and you're not going to get 100% on the homework assignment, but don't see it as a failure of your own coding abilities, but just kind of areas where, you know, you have to kind of work on to get stronger. Okay. You know, if we have to, if we have to, you know, we do report, you know, issues of plagiarism and stuff to the dean's office, and it's something I don't enjoy doing. It's a huge kind of pain, logistical burden, and emotional burden. It's not something that I enjoy, but it is something that I am willing to do, you know, for the sake of the kind of integrity of the course. So, but you know, of course, my preference is just see the homework assignments as learning opportunities. Think of it as going to the gym to work out to make yourself stronger and better as far as becoming a better coder. And I think of it, and I think that's an important kind of attitude and approach to kind of any kind of learning experience. Okay, I put in a bunch of slides for like what kind of collaboration is allowed and what's not allowed. And basically it can just be summed up with don't show each other's code, okay? You can ask questions. You've got CampusWire, you can ask questions. And there's lots of ways to answer questions on CampusWire without actually writing code up on the assignment. So you can ask, how did you approach this problem? And you can respond with, I used this function without writing the code for actually doing, you know, how to actually set up the function or the loop or whatever it might be, okay? So anyway, here's just a bunch of stuff. And in my slides, I do put code, and of course you are, you're allowed to discuss any of the code, and you can write code on CampusWire, any of the stuff that's, you know, for questions and discussion, just not, don't write code if it's related to a homework problem. Okay, so that's kind of the line that that I'll draw, is that, you know, if I put code in my slides, you can copy that code onto CampusWire and ask, you know, what exactly is this line doing? You know, what's going on here? That's all fine. Okay. It's just if it comes to a homework problem or something like that, don't put your code up on CampusWire there. Okay. And you can ask questions about the homework, and there's lots of ways to answer a question that don't kind of break these rules. All right, and just as far as, you know, before we get kind of started on, I guess, lecture content and whatnot, I do want to say, you know, your health, that is your physical, mental, spiritual, and emotional health, all of that is far more important than your grades, okay? And I want you guys to take care of yourself. You know, make sure you guys get sleep. Make sure you are, you know, with being doing distance learning and you know, social, physical distancing, all of that. It's also easy to feel isolated and depressed, and so I want to kind of encourage you to do activities that will strengthen your mental health, in terms of just you know, do some exercise, try to have conversations with friends and connect with other people, even if it has to be you know, not in a, you know, not face to face, even if it has to be done online. I think it's important for as us as people to connect with one another. If something happens during the quarter, you get sick or you experience some kind of some issues and things like that, you know, let me know. I try to be flexible and accommodating within reason. And, you know, I see it my job as a teacher. My responsibility is to teach you guys, but I'm also here to support you as well. So, so please, you know, this has been a crazy year. It feels when we had to kind of begin doing distance learning at the end of winter quarter, and so that was over. That was like over 6 months ago, and it just feels like it's been a very long time. I you know, spring quarter was entirely online, and then I also taught summer session entirely online, and I don't know how much longer we're going to be doing online learning, but it seems like it's you know, at least all of this quarter, and it looks like next quarter as well. I'm not sure. So it might be a while before we get to see one another face to face. But I hope you guys are doing okay. Are there any questions before we get started, as far as 102C goes? How are you guys doing? All right, Roger gave me a double thumbs up, so that's good. But all right, okay, and some of you guys are giving me thumbs up in your reactions. All right, I mean, I genuinely hope that's the case. I know sometimes it's a lot easier to just, if somebody says, "How are you doing?" Just to kind of give me a nod and a smile and a thumbs up. But you know, but inside, you know, to be struggling emotionally. And I mean, to be honest, it's been a struggle for me as well. I'm a little bit more extroverted in that I enjoy the company of other people, and so this whole quarantining and social distancing thing has been kind of hard for me. You know, I'm thankful for you know, my family, and they fulfill a lot of my emotional needs, but yeah, I miss kind of just having conversations face to face with my students. That's like one of the best parts of this job. So so anyway, I hope you guys are doing okay. All right. I'm going to just do a very, very, very quick introduction to, kind of what is this class all about? And we'll talk about that. We're not going to really get into a whole lot of heavy stuff. There's going to be some stuff will look a little bit heavy, but it's just kind of review from other courses. And then this first weekend, just take it easy. Your first homework assignment I'll probably post on Monday. Okay, so don't even worry about homework just yet. Just take this first weekend. I don't know. Did you guys have class yesterday? Any of you? Some of you? Okay. All right. So we're already starting to get back in the swing of things. So anyway, this class is titled Monte Carlo Methods. Okay, and so Monte Carlo methods the idea is it uses repeated random sampling to estimate a numeric answer to a problem that would be difficult to answer analytically. All right, so that's kind of the summary of this. Oh, by the way, I'm using two screens, so I don't know if you're looking at where I'm looking, but when I look over here, I'm looking at the slides that I'm presenting to you, and then I have all of your faces on this screen, so I can look at you guys. And anyway, so this is Monte Carlo methods. We're using random sampling, and we generally harness the power of the computer to do the random sampling, and we estimate numeric answers. So everything that we get is going to be an estimate. We're not going to get exact answers, but these are going to be good estimates of something that's going to be kind of a difficult question to answer using kind of your traditional mathematical tools. So if you look up if you go on Wikipedia and you look up Monte Carlo methods, there's a little bit of, it's a fascinating history how this came about, okay? And so kind of credit is given to Stanislaw Ulam. I believe he was Polish. Ooh, okay, maybe I'm gonna get in trouble for making up people's ethnicities. Okay, but this, scientist, mathematician, researcher working on the Manhattan Project, for the atomic bomb at Los Alamos National Laboratory. So this is, top secret stuff, height of World War II, okay? And, they had to do calculations for kind of like how much energy would be released with this kind of amount of, nuclear reactive material and stuff. And the scientists were having trouble trying to figure this out using kind of the conventional mathematical methods, because there's a random element. If you go down to the nuclear level, there's random elements in terms of like, how much stuff I don't know too much about nuclear physics, but like it's radiating energy and stuff like that. And it gets the conventional mathematical methods were difficult, okay, to solve. And so our scientist, he was inspired by kind of a question that he had come up with when he was sick and just kind of playing solitaire games by himself. Okay, so this is what people had to do before they had apps on their phone and stuff like that. Is when you were sick and stuck in bed, you dealt yourself card games of solitaire, and you played these card games by yourself. And so one of the questions he had was, what's the probability that a random deal of this card game would be winnable? And he originally thought like, okay, I bet I can do the math behind this, right? After all, there's only 52 cards or whatever, and we can try to do the math. And just like in poker, you can do a bunch of calculations to figure out the probability of something happening. But the math got really hard, okay? And he thought, well, instead, maybe it would be easier to just shuffle the deck, try playing 100 different games, and then just keeping track of how many games I win and how many games I lose. And that should at least give me an estimate of what percentage of games are winnable. Maybe, it's going to take a while to deal out 100 games and play through them. But, if let's say he wins, 62% of the games by doing this, by playing 100 random games, that should at least be some estimate that, you know, might not be 100% accurate, but should be at least in the ballpark of the answer. And that's basically the premise of Monte Carlo methods, is that rather than trying to do the calculations, just simulate the outcome. Okay, and so he explained this idea to his colleague John von Neumann, and John von Neumann was kind of the coder, and he coded it into the ENIAC mainframe computer. So kind of you know, this is the, you know, in the 1940s. So they had this big machine, and they coded it in there. And because all of the work on the atomic bomb was super secret, they had to use a code name. And so they picked Monte Carlo, named after the Monte Carlo casino in Monaco, which is, you know, kind of where James Bond goes to play his casino games, to play Baccarat or whatever it is. Kind of just this idea of like random things happening and all the time. So the history behind this, I think this is really fascinating and stuff. So, and this is just your one-page Wikipedia summary, but I'm sure you can read more about this. Okay, so just kind of to put this in the context of statistics and probability and stuff like that. Okay, this is just kind of a recall. You know, let's go back and revisit Stats 100B. Okay, so I'm assuming everybody here has taken Stats 100B, right? That's a prereq for this class, and you're not allowed to be in here if you haven't taken it. So so anyway, you know, in 100B you had to do math, and you know, some of it would be to try to find the properties of some kind of probability distribution here. Sorry, let me just close this door over here. And so, you know, let's say you have some random variable x. Okay, the random variable x comes from a probability function, from some kind of distribution with a probability function f of x, right? And so if it's continuous, then you know, how would you calculate the expected value of this distribution? What's the integral that we use? You guys remember this? Okay, so it's mu is the expected value of x, which is basically the integral of x times f of x, and this is, you know, over kind of the domain or support of x, right? So wherever x is not 0, you take the integral over that area, and it's the integral of x times f of x, right? So if you have the normal distribution, then the domain of x or the support of x is -infinity to infinity, whereas if it's like a binomial distribution, goes from 0 to 1, or if it's I don't know, chi-squared, it's 0 to positive infinity and things like that, right? And if it's a discrete distribution, instead of an integral, what do you have? You have a summation, right? So thank you for writing that sigma sign, and exactly, you just get the summation of, you know, x sub I times f of x sub I for basically all of the different values that x sub I can take on. Okay, so this is what you have for calculating the expected value. All right, what about the variance? Do you guys did we all forget, or do we?
Isn't it like x squared f of x dx?
Yeah, so it's x minus mu quantity squared. So you take the expected value of basically the squared distance from the mean. Okay, so if you just think of the variance is the average or expected squared distance from the mean. So you take, you know, what's the distance from the mean? That's going to be x minus mu, and that distance squared is x minus mu squared, and what's the expected value of that? And then, you know, one of the most fundamental kind of identities that you have to prove in 100B is that this quantity is equal to this quantity and things like that. But anyway, basically, we're going to just take the integral over x minus mu quantity squared. So you have to find the expected value from the, you know, in a earlier step, and you multiply that by the probability function, and you take the integral of that thing. Okay, and if you have the discrete version, or if you have a discrete random variable, you know, you replace the integral with a summation. Exactly. So. And so that's the variance of a random variable, okay? And in general, if you have just any arbitrary function, say g of x of a random variable, then the expected value of, you know, the function applied to that random variable is going to be the integral of the function applied to some value of x multiplied by the probability of getting x, right? So multiplied by the PDF. And so, you know, this allows you to kind of calculate expected values of, you know, any kind of distribution that you can think of, and any kind of function of a random variable. So, you know, plug stuff in and you'll get answers here. And in 100B, basically, you had to do all of the kind of the analytic math, right? And you would either do the integrals or you would use other functions like the moment generating function and things like that to calculate values like the mean and values like the variance or other stuff, okay? So, you know, in a lot of problems, in many cases involving probability distributions, that integral or the sum, if it's like a big sum, can become too complicated to try to solve analytically, right? And so instead of trying to get the exact analytic answer, what we can do is we can get an estimate based on simulated randomness, right? So rather than trying to work through the math, the whole point of Monte Carlo methods is to kind of avoid that hard math, okay, or find a workaround to those difficult math problems. And the disadvantage is that you're not going to get the exact answer, but the advantage is at least you can get an estimate of the answer. And that's really the big picture. Okay, so if you say, well, what's Monte Carlo methods about? It's this slide here, right? So a lot of times we have problems that rely on some kind of random variable, but the math and the calculations behind it are hard, right? And so we're not going to bother, okay? And in some cases, it's not just hard, but it could be impossible, right? It could be impossible, right? Like we know some integrals are unsolvable, and you could end up having a situation like that. So question, what keeps us from using gradient descent algorithm or opt-in function to solve these complex integrals? Well, not all of these problems can be turned into an optimization problem, right? So in the optimization problem, you're trying to find where some function has a maximum or a minimum value, right? So in like if you took 102b, okay, which you're not required to have taken, okay? So in this class, you only need 102a and you can take 102b later. But in 102b, that class is all about optimization and it's trying to find where the function has a maximum or a minimum, okay? But an integral is not necessarily, like the solution to an integral is not necessarily going to be a maximum or a minimum. And you can't necessarily turn the, like you're trying to solve an integral, but the answer to that integral is not necessarily the maximum of a different function, okay? And so, so in these cases, you know, Optim is not going to be able to help you because it's not you're not searching for a maximum or you're not searching for a minimum. You're just searching for the answer to an integral, and so we need some way to kind of to get the answer to the integral, and we might not be able to do it directly. And so the So an approach is to use Monte Carlo methods. Okay. In general, Monte Carlo methods are inefficient. Okay, so that's an important thing. Like, you shouldn't use Monte Carlo methods if the analytic approach is available and easy. Okay, if you can do the analytic approach and it's available and easy, just generally use it. Okay, do that. But if it's either not available because the analytic approach is impossible, or if it's not easy and it gets really complicated, then Monte Carlo, which is kind of a inefficient brute force method, could be a viable option. Okay, so simple example is, let's say you have some random variable x, okay? And let's say we're able to simulate draws of this random variable, okay? And so the question could just be, well, what's the mean of the random variable x, right? What is the mean of the random variable x? All right. And what we can do is, rather than having to do the analytic approach, is that we can just take a random sample of, say, n values drawn from that distribution defined by f of x, and then you can estimate the mean by taking the mean of the sample. You just take the sample mean, of your random sample, and that's going to serve as an estimate of the mean of the entire probability distribution. And that's kind of the basic premise. I mean, we could end the class here, and you would have gotten the gist of Monte Carlo methods. Okay, don't worry, we're going to spend the whole 10 weeks talking about Monte Carlo methods, but this is basically the gist, right? It's just, you've got a random variable. What's the mean of the random variable? Okay. Instead of doing the analytic approach, we're just going to generate a random sample of that variable, and then we're going to take the mean of that sample. So the estimated mean, mu estimated, is just going to be the sample mean of your xi's. So, all right, so here's a question. What is the mean of a chi-squared random variable with 5 degrees of freedom? All right, so you guys learned the chi-squared distribution in 100B, right? Okay, so, well, okay. Whoever wants to, you can unmute yourself. What's the chi-squared distribution with 1 degree of freedom equal to?
Normal squared?
Yes, it's a normal random variable, right? You take a normal random variable and you square it, right? And so we know in the normal distribution, the 0 is the most common value, but a lot of values, between -1 and +1 are common. And basically you just take a random normal variable and then you square it, and that's going to be the chi-squared distribution with 1 degree of freedom. What's the chi-squared distribution with 5 degrees of freedom? How do we get that?
Is it the summation of 5 normal?
Yes, so we do, you basically do 5 of these chi-squared random variables, and you kind of add them together, okay? All right, so what's the mean of the chi-squared random variable with 5 degrees of freedom? I don't know, is this an exercise you had to do on 100B? Maybe does it sound like something you might have had to do on 100B? Okay, and if you recall the kind of the relationship, yeah, the answer is going to end up being 5. The mean of a chi-squared random variable is just equal to the degrees of freedom. But the process to solve it, you'd have to look up, okay, well, what was the PDF of the chi-squared distribution? And it's something like this, where k is the degrees of freedom, and it's like 1/2 raised to the k over 2 times gamma of k over 2 times, x raised to the k over 2 minus 1, and e to the negative x over 2. That's the PDF of the chi-squared distribution. And then, attendance quiz answers. I should give you some. Okay. All right. I'll give you the first 2 attendance quiz answers, and I'll give you your last. Okay. Let's forget. Okay. We'll give everybody the attendance quiz answers. Today's attendance quiz answers are E, C, and A. I'll give you all 3 of them right now. Okay. So elephant, cat, apple. That's going to be the attendance quiz answers for day. I have to create the attendance quiz on CCLE. So just give me a moment for creating the attendance quiz or the viewing quiz, and that will be so again the answers are elephant, cat, apple. ECA, elephant, cat, and apple. Okay, so this is the PDF, and if you tried to do this analytically, like this would be the approach that you would probably take in 100B, is you'd have to use something, you'd have to figure out the moment generating function, which is kind of a process in of itself. I don't know if this is triggering bad memories or maybe this was a good time, but and this is just slide, or this slide is just review. I'm not going to be testing you on the moment generating function or anything like that, but you'd figure out the moment generating function of the chi-square distribution, which is this. And then the mean is equal to the first moment, which is the first derivative of the moment generating function. You know, if I remember all of my 100B math correctly, and it would look something like this, right? You take the derivative of this, and then, you know, you apply chain rule. And then when you do this, you're going to end up getting K. The mean is equal to K, the number of degrees of freedom. So for a chi-square distribution with 5 degrees of freedom, the mean is going to be 5. All right. Is that all right? I hope that I went over this quickly, but hopefully this just kind of sounds like, okay, sounds reasonable. This is how you would do it via Monte Carlo. Okay. What's the mean of a chi-squared random variable with 5 degrees of freedom? Well, you would just say, let's pull out 100,000 values. So I'm going to set n equal to 100,000. And I'm just going to generate a sample of 100,000 values drawn from the chi-squared distribution. So I use r chi-squared. Say I want n of these, 100,000 with degrees of freedom equal to 5. This creates my sample. And then the estimate of my mean is just going to be the mean of my sample. So I say, what's the mean of my sample? And I get 4.993. Okay. And so it's close to the analytic answer. The analytic answer is 5. And via Monte Carlo estimation, I get an answer that's close to it. Okay. So that's an important thing. You're not going to get a formula. You're not going to know that the mean should be equal to K, but you're going to get an approximate answer to the thing, which is it's approximately 5. It's 4.993. And if you don't do the analytic answer, you don't know if this number is too high or too low. Okay, you're just going to say, okay, it's got to be, the mean has got to be something around 4.993. Okay. What if we want to know the variance? Okay, well, you could go through the analytic approach. Okay, but again, for the for Monte Carlo estimation, you have your sample of 100,000 values drawn randomly from the chi-square distribution, and so you can just say, well, the estimated variance is just going to be the variance of my sample. Okay, and we get something like, we get 9.9789. Okay. And the true answer is 2 times your degrees of freedom. The true variance is equal to 10. And here's our estimate. So our estimate's pretty good. And in my opinion, this is very easy to do, right? Because we have a computer that can generate chi-squared distribution variables very easily. And if we get a sample, we can just plug that into something like the mean or the variance, and we can get estimates of the mean or variance of some kind of distribution. Okay, not exact values, but we're getting good estimates. And here are just some kind of things that that we see in Monte Carlo methods. So I don't know if you've heard of 538, but it's a kind of a blog that does sports and political analysis. And so here's kind of their current analysis of the election. And this is based on, okay, so when it comes up with some kind of probability, okay, it says we simulated the election 40,000 times to see who wins most often, okay? And so this is based on, because there's no formula. There's no formula right now that just says plug in whatever and you get this answer for, you know, what the probability somebody's going to win. And so this is basically they've done a whole bunch of simulations, and based on the simulations, you know, right now, Biden has won around 79% of the simulations, and Trump has won around 20% of those simulations. Okay, and that's just kind of what the simulations have shown. This would be a Monte Carlo method. Similar thing for right now. It's the NBA Finals, and they're looking at, you know, what's the probability of the teams winning or losing. I'm a big Lakers fan, so this is very exciting for me. But it says these forecasts are based on 100,000 simulations. Okay, so this is a Monte Carlo method. There's not an answer that's there's no formula or no math model that just straight up exists, but they are able to build up some kind of simulation. If you took Stats 102A with me, one of my homework assignments was simulating the board game of Monopoly, and you had to figure out which spaces get landed on most frequently. That is effectively a Monte Carlo simulation, because rather than trying to multiply a whole bunch of probabilities, which is theoretically possible to do, it is possible to do that and figure out the probability that somebody lands, you know, on Boardwalk or whatever. We just coded up the rules, and then we had the computer run many simulations to get an approximate answer. And that's basically a Monte Carlo method. There's Monte Carlo methods in finance, which basically simulate, you know, basically random fluctuations in market prices and things like that. And you can read about that. Okay, so this just again sums up that that it's useful in getting answers when the math gets messy. It's extremely useful for Bayesian statistics, okay? Because in Bayesian statistics, we're going to get big and messy integrals, and it's also useful in high dimensional settings, all right? And so that's where we're headed for the rest of the course, okay? So the big idea is, so next week, we're going to, I'm going to start introducing Bayesian statistics concepts, and that will kind of provide kind of a baseline for what application we're going to do. So rather than just jumping straight into Monte Carlo methods straight away, I'm going to kind of set up the background with Bayesian statistics, because this is probably the most common application for Monte Carlo methods because of how complicated the integrals go. So anyway, I'm looking forward to this quarter with you guys. I miss seeing you guys in real life, but this will do, and I'm looking forward to a good fall quarter. So we'll end here for today. Sorry for going a few minutes over, and we will see you guys on Monday. Have a good weekend, you guys.